Pluto, a distant and enigmatic dwarf planet, was once considered a part of our solar system's planetary group. However, recent startling revelations from leading astrophysicists like Neil deGrasse Tyson and Michio Kaku have thrust Pluto back into public attention. These experts have raised an alarming theory. They claim Pluto might be on a potential crash course with Neptune. But how could such a dramatic event unfold, and what would the ramifications be? Is this a rare cosmic phenomenon, or could there be deeper reasons behind this alarming forecast? Join us as we investigate the possibility of a Pluto-Neptune collision. Although Pluto was reclassified as a dwarf planet due to its strange orbit, it continues to be a subject of fascination and analysis in the field of astronomy. Recent forecasts from prominent scientists suggest that Pluto's orbital path is dangerously close to Neptune's. Both Neil deGrasse Tyson and Michio Kaku have voiced concerns about a potential collision between the two, which could have serious consequences for Earth. How is this even possible? Pluto's orbit around the Sun is unlike any other planet in the solar system. It takes an astounding 248 years to complete one full orbit, meaning that since it was discovered in 1930, it has not even finished a single full cycle. But the intrigue doesn't end there. Pluto's orbit is highly elliptical, meaning it deviates significantly from the near-circular orbits of the major planets. What's even more unusual is its inclination, angled at 17 degrees to the ecliptic plane. This steep trajectory stands in stark contrast to the orbits of the other planets. Perhaps one of the most remarkable features of Pluto's orbit is its intersection with Neptune's. For about 20 years of each orbit, Pluto actually passes closer to the Sun than Neptune, defying expectations based on their positions in the solar system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. Studies of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to comprehend its unusual trajectory. Unlike the orbits of other planets that lie fairly close to the ecliptic plane, Pluto's orbit is distinguished by its steep angle and elliptical shape. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's. Despite this apparent risk, Pluto's orbit has remained stable over time, highlighting the complexity of space mechanics. The three-body problem in physics, understanding how three celestial bodies, like Pluto, Neptune, and the Sun, interact under gravity, explains why Pluto's orbit is so stable. In theory, Pluto's orbit should be chaotic, with minor variations in its initial position leading to major differences over millions of years. However, computer simulations in the late 1980s revealed that despite its chaotic potential, Pluto's orbit remains stable over vast periods, effectively keeping any disruptive effects in check. Research has also shown how larger planets, like Jupiter, Saturn, and Neptune, influence Pluto's path. Jupiter's immense gravitational pull is powerful enough to maintain Pluto's orbit for billions of years. These cosmic interactions are crucial for the structure of the universe. Without them, the solar system could be much more chaotic and unpredictable. Pluto's orbit provides a fascinating example of how celestial mechanics work, showcasing both stability and potential chaos within our solar system. The unique nature of Pluto's orbit, especially influenced by Neptune's gravity, demonstrates the intricate and ever-changing dynamics of space. Predicting future cosmic events, particularly involving chaotic orbits like Pluto's, remains a significant challenge. The inherent unpredictability of such systems makes long-term forecasts uncertain. Numerical simulations help us better understand and predict the movement of celestial bodies, but they also highlight the limitations of our ability to foresee everything. So why are leading astrophysicists like Tyson and Kaku just now raising concerns about a possible collision between Pluto and Neptune, despite all these stabilizing factors? Tyson and Kaku, both highly respected figures in the field, have raised alarms about a potential catastrophic event involving Pluto and Neptune. If these two planets were to collide, it would be a highly unusual and devastating occurrence in our solar system. The collision would release vast amounts of energy, potentially shattering Pluto, due to its relatively small size and icy composition. The debris could spread throughout the solar system, posing threats to other planets and moons. For Neptune, the impact could alter both its atmosphere and possibly its orbit, depending on the nature of the collision. Michio Kaku, a theoretical physicist known for his work in string theory, offers an additional perspective on the potential consequences. His expertise in theoretical physics helps frame how a Pluto-Neptune collision could shed light on larger questions about celestial mechanics and string theory. By studying the gravitational interactions and orbital movements of planets like Pluto, scientists can gain valuable insights into the dynamics of the solar system and even plan for future space exploration missions. This knowledge could help us navigate the complexities of space more effectively, predict potential hazards, and inform missions that explore the farthest reaches of our solar system. The interplay of celestial mechanics and theoretical physics is integral to understanding the behavior of planets. If Pluto and Neptune were to collide, it would be a monumental event in astrophysics, potentially providing rare observational data that could relate to the concepts of string theory. String theory, which posits that the fundamental building blocks of the universe are one-dimensional strings rather than point particles, attempts to unify all the forces and matter of the universe. A collision of this scale could lead to extreme conditions of energy and gravity, allowing scientists to observe phenomena that string theory predicts, such as the behavior of particles and forces under intense conditions. Though the direct impact on Earth would be negligible due to the vast distance between us and the outer solar system, the scientific ramifications of such an event could be profound. It could contribute to our understanding of the universe's fundamental nature, as described by string theory and other areas of physics. Pluto's orbit offers a fascinating case study in celestial mechanics, showing how stability and chaos can coexist within the solar system. Pluto's orbit also shows the importance of understanding the complex gravitational interactions that shape the movements of celestial bodies. The three-body problem is only one of many unresolved mysteries in the universe. Numerous other potential cosmic disasters have been predicted, emphasizing the constantly changing and unpredictable nature of space. Studying these patterns helps us understand planetary motion, especially when planets come extremely close to one another. Rogue planets, for instance, are wandering worlds that have been ejected from their star systems due to gravitational disturbances or other cosmic events, such as the close passage of another star. These rogue planets travel vast distances, potentially entering other star systems, and there is a small chance they could collide with planets in those systems. However, space is incredibly vast, and the odds of a rogue planet directly hitting another planet are extremely slim, given the enormous distances involved. Despite the low probability of these events, the mere existence of rogue planets adds an element of unpredictability to the cosmos. Pluto's mysterious orbit around the Sun continues to captivate both scientists and the general public, offering a glimpse into the complexities of space mechanics. Although its reclassification as a dwarf planet sparked debates, it remains an object of significant scientific interest. The recent focus on its orbit has reignited discussions about its place in the solar system. Astrophysicists like Tyson and Kaku have brought attention to the possibility of a Pluto-Neptune collision, shedding light on the delicate balance of forces that govern our solar system. Pluto's orbit, with its eccentricity and steep inclination, defies conventional expectations, challenging our understanding of planetary motion. Unlike the relatively circular orbits of other planets, Pluto's path intersects with Neptune's at certain points in its long journey around the Sun. The gravitational influence of nearby planets, especially Neptune, plays a critical role in shaping Pluto's orbit, ensuring its stability over long periods, despite the chaotic potential of its path. This is a key area of study for astronomers, as it helps reveal patterns and mechanisms that prevent catastrophic collisions in our solar system. The three-body problem involving Pluto, Neptune, and the Sun exemplifies the intricate gravitational dance that governs planetary orbits. Understanding these dynamics requires advanced mathematical models and computational simulations. These models give us important insights into how planetary orbits evolve over time. Pluto's reclassification as a dwarf planet has sparked ongoing debates about the criteria used to define planets, as well as the diversity of celestial bodies in the solar system. While Pluto's size and distant orbit set it apart from traditional planets, its importance as a celestial object remains significant. Research into Pluto's orbit provides valuable lessons that extend beyond our own solar system. The study of planetary orbits, gravitational interactions, and theoretical physics is essential for understanding astrophysical phenomena on a larger scale. String theory, which seeks to unify the fundamental forces of nature, offers a framework through which scientists can interpret events like a Pluto-Neptune collision. The aftermath of such an impact could provide valuable data on gravity, spacetime, and gravitational waves, areas central to string theory. Though the likelihood of a Pluto-Neptune collision is speculative, its potential scientific implications highlight the interconnectedness of celestial phenomena and the ever-changing nature of the universe. The ongoing study of planetary orbits, gravitational interactions, and theoretical physics is key to expanding our knowledge of the cosmos. Pluto's orbit, with all its peculiarities and anomalies, invites exploration and inquiry, offering a glimpse into the wonders and complexities of space. As we peer deeper into the cosmos, we are reminded of the vastness of the unknown and the endless possibilities for scientific discovery. Pluto's enigmatic orbit serves as a reminder of the mysteries that await exploration in the ever-expanding frontier of space. The study of celestial bodies and their interactions continues to shape our understanding of the universe, offering opportunities for future discoveries that could transform our comprehension of the fundamental laws of nature. Pluto's orbit, with its unique characteristics, continues to captivate scientists and astronomy enthusiasts alike. Its path through the solar system is an ongoing source of study, offering insights into the dynamics of space, the role of gravitational forces, and the complexities of planetary motion. While its status as a dwarf planet has reshaped our understanding of what constitutes a planet, it remains a compelling object of interest, providing a fascinating window into the forces at play within our solar system. As Pluto continues its long journey through space, its interaction with Neptune and other planetary bodies serves as a reminder of the delicate balance of forces that govern the movements of celestial objects. The study of these interactions is vital for gaining a deeper understanding of the intricate dynamics that shape the solar system. Despite the many mysteries that still surround Pluto's orbit, we are gaining valuable knowledge about the forces that affect all planets, large and small, and the ongoing evolution of the solar system. One of the most remarkable aspects of Pluto's orbit is its stability despite its chaotic potential. Over time, scientists have developed increasingly sophisticated models to predict the future movements of celestial bodies. These models have proven essential in helping us understand the long-term behavior of planets like Pluto. The fact that Pluto's orbit remains stable, despite the chaotic tendencies of its path, is a testament to the complex and highly regulated nature of the solar system. As researchers continue to explore Pluto's orbit, the potential for future discoveries remains immense. The insights gained from studying Pluto's trajectory could have profound implications for other areas of space exploration, including our understanding of other distant worlds. By understanding the forces that govern Pluto's path, we can apply these principles to other celestial bodies, gaining new perspectives on the universe's mysteries. Looking beyond Pluto, the study of other rogue planets, those wandering through space without a star, offers an additional layer of intrigue. While the chances of these planets colliding with another celestial body are slim due to the vast emptiness of space, the mere existence of these rogue worlds raises important questions about the stability of planetary systems and the potential for interstellar encounters. These wandering planets, once part of a star system, continue their solitary journey through space, carrying with them the potential to intersect with other star systems. Though the likelihood of direct collisions is low, their presence serves as a reminder of the dynamic and unpredictable nature of space.